Okay, so this is the part we left off yesterday, and I want to make sure you understand it. This part right here should be x. If it was a normal problem, it would just be log base 7 of x. And that part would tell you where the asymptote is. So at this point, I need to take a little bit of time to make sure you understand what logs really look like. So go off to the side, and would you please make a standard log graph, and it looks like this. I sometimes will say it looks like a tree, a red tree in this case, that's been blown over in the wind. That's what a log really is. They're not, when you're standing up, when trees are standing up, you don't say, oh, look at the log with the pretty leaves. No, it's only after the tree blows over in the wind. Okay, so it's a dumb way to remember it, but it's a way. Remember it your own way. That's what logs look like. Now, just to clarify, there's a couple important spots. It goes through that spot, which is 1, 0. Now, why would it? Let's look at what a log looks like. Y equals log base, let's say, 3 of x. Why would, when you put a 1 in for x, why would you end up getting 0? You've won the argument. Do you remember that dumb little thing from yesterday? When you won the argument, you get nothing. The answer is 0. That's why 1, 0 is a point that's always on a log graph. Now, always is a pretty strong word. Always, unless you've moved it. Like, do you get if I go and put minus 3 on the inside? That's going to move the whole thing over, right? 3. You know what I'm saying? Okay, so the asymptote, without me moving it, the asymptote would be at 0. What makes that 0? So if they change the problem to say like 2x minus 1 in there, the asymptote will be at where 2x minus 1 equals 0. So all you have to do is take the argument part, set it equal to 0, and solve, and you'll know what x is for your asymptote. I'll show you. This one would have been moved to the right one and had a stretch, oh wait, it's on the inside, shrink factor of 2 in the horizontal direction.
Wouldn't it be 1/2?
You're right. When I said shrink, I should have changed it to 1/2. Good point. So a shrink factor of 1/2 in the horizontal direction, and you're probably thinking, well, I have no idea what that would look like. It's okay. All I need you to be able to do is go, the thing in there will give me the asymptote. So plus 1, 2x equals 1, x equals 1/2. Oh, so you're saying there'd be an asymptote at 1/2. So instead of the asymptote being at 0, it's going to be over here a little bit at 1/2. Now, if you needed exact points on it, I hope you remember that the XY chart is your best friend in graphing. I still count on the fact that you can find points if you need to. So let's try that on this one. Would you agree that if it was log base 3 of 3, it would work out really nice? What is log base 3 of 3? It's 1. So do you get, I'd like it if the inside was equal to 3? Do you get how it would be nice if 2x minus 1 was equal to 3? That sounds like an equation. 2x minus 1 is equal to 3. Add 1 to both sides. 2x equals 4. X equals 1/2. Okay. Apparently, x equaling, whoop, did I do something wrong? Oh, sorry, 4 divided by 2 is 2. Sorry, not 1/2. 2. X equals 2. I should have done the last step, and I wouldn't have done that. 4 over 2 is equal to 2. Whenever you try to skip a step, it's dangerous. All right, so that is what? That would be a nice thing to put into this function. If I put a 2 in, then I would get log base 3 of 3, and therefore I'd get a 1. So 2, 1 is on this graph. All right, I'm going to see if you really understood that. I'm going to give you a new one. Y equals log base 4 of 4x plus 2. Tell me two things. Where's the asymptote? And just find me 2 points that are on this log. Hint, if you make this 4, that'd be a nice point. Not put in 4 for x, but put in something that makes this equal to 4. All right, pause for a second while you give that a try. Okay, let's see how you did. First of all, set that equal to 0. Why? Because if there was a 0 right here, think about it, log base 4 of 0 wouldn't exist. You're not allowed to have a 0 there. Do you remember how those numbers need to be positive? So the domain of a normal log is from 0 to infinity, but it can't be 0. That spot right there, if x is in this spot right here, you can't have it be 0. That's why there's a parenthesis there. Okay, so we're trying to find where it would be 0. So we set 4x plus 2 equal to 0. Negative 1/2 again. So x is negative 1/2. You can put it on your chart if you want and try putting it in, and you'll end up getting a 0 in the argument. So that's not possible. That's the asymptote. Just to clarify, there's a lot of things that would have killed this function, but 0 is the one you want to find the asymptote. So you set this part equal to 0. And then it's always that to infinity is your domain. I'll say that one more time. So we just solved that and we got negative 1/2. Then my domain for this function would be from negative 1/2, which is the right on the edge of working but doesn't work, all the way to infinity. Okay, then what's some points that are on it? All right. Dice of destiny. Hopefully, you guys stuck in some numbers for x or y and figured out some points. Row 2, last person. In the back. You don't know? All right, then I get to walk you through it. I'm going to help you. If it says log base 4, what would be really nice if it was there? Inside the parentheses. What would be nice to have in there? If I just had log base 4 of x, I'm asking you what number would be nice to have in here, not a variable, a number. All right, I'm going to go off to the side and say, if it was log base 4 of some magical number, anything you want right there, what would be an easy number to have? 2 is not an easy number. Let me explain why. Because log base 4 of 2 doesn't work out nice. Log base 4 of 4 would work out nice. So this is the ideal thing to have there, would be log base 4 of 4. Do you know what log base 4 of 4 is equal to? Okay, so this goes back to one of our properties and one of the things that you need to know. If these two numbers are the same, then the answer is whatever the power is. This answer would be 1. All right, everybody, if I said log base 3 of 9, then that's really log base 3 of 3 squared. So what's the answer? 2. So if you can get these numbers to be the same, that's your goal. Okay, so I'm going to ask again, if I have log base 4 here, then what would the ideal number be to put right there? 4. Okay, so if I want a 4 to be there, what's actually there is 4x plus 2. So I got to get that to be equal to 4. So if 4x plus 2 were only equal to 4, then my answer would be easy. So that's what I do. I set it equal to 4. 4x equals 2. X equals 2/4, also known as 1/2. All right. So if x equals 1/2, it'll work nice. Now I'm going to go put that in my chart. Negative 1/2 made the asymptote, but positive 1/2, when I put it in, gives me log base 4 of 4, because that's all 4. And what is log base 4 of 4? Person in the back who's still doing this. Not going to say your name on the video. 1. Excellent. 1/2 comma 1 is one of your points. All right, I'm going to give you one more example on that. If you had log base 4 and you'd already used up 4, because we already did that, what's another nice thing that would be handy to know? 16, I like it. Because if you had a 16 right here, do you get how that would be log base 4 of 4 squared?
Yeah.
That's why 16 would be great. So I want this to be 16. So I say 4x plus 2 needs to be 16. 4x needs to be, take away 2, 14. X needs to be 14 fourths, which seems like so complicated. Why would you pick that? Because 14 fourths will give you exactly 2 for a y value, because this part will be 16 and it'll be log base 4 of 16. Okay, 14 fourths is the same as 7 halves. I just noticed that. It'd be totally fine to say 7 over 2 or 3.5. So 3.5 comma 2 is another point on this graph. All right, so how do you graph these things? Find the asymptote, find a couple points, and you're good. If you know that the asymptote runs here and that there's a couple points and they're like there and there, it's not going to be real hard for you to figure out what the log graph looks like. Find the asymptote, find a couple points. Okay. All right, so back to the problems that we started with on this page. What if I set this equal to 0? What would I be finding? Yeah, they'd be roots, but they would be what of the graph?
Asymptotes.
They would be the asymptotes of the graph. If you set this equal to 0, does it sound like a quadratic set equal to 0? I can do that. We've done that before. If you can factor it, you should. But if you can't factor it, you could always use a quadratic formula, and you'd be finding the asymptotes. Could you find other points on the graph? Yep. This doesn't have a base, Mr. Server. It's a flaw in the problem.
10.
No, it's base 10. And so it'd be ideal if this thing were equal to 10. That's one of the things I'd try to put into my XY chart. How do I make this all equal 10? I set an equation and I set it up so that that equals 10. And I figure out what x has to be. All right. I know that got a little intense. So what's the homework like for tonight? I'm going to do a little bit of review now of what you were supposed to learn yesterday. This was the add-on thing. Basically, set that equal to 0 and you'll find the asymptotes. Okay? So what else do I need you to know? I'm going to show you what your homework looks like. There's where our homework starts. And it's talking about exponentials. You barely know that logs go like this. Do you even know what exponentials look like? All right, so I'm going to teach you about what exponentials look like. And then this same exponential gets moved, that looks like down 1. Does that make sense? If you knew what the exponential looked like. Well, remember, what's your best friend in graphing? XY chart. You could always use an XY chart and figure out some points that are on 2 to the x. That would be a great way to do it. But I also want you to know what the parent function looks like. So we'll talk about that. That's one of the things for today. So we're going to do this page. You'll see. Another thing for today, and this is just all more complicated moves, like, oh, it got vertically reflected and moved right too. But you got to know what the parent graph looks like in the first place before you know how to move it and flip it. Okay, and then this is finding an inverse. That's the other thing I got to teach you today. And I'll remind you how to find an inverse. It's really not that hard. Go off to the side and make this. This is the key thing for understanding today's. That's an exponential. That's a log graph. And they are a reflection of each other across the line. Who remembers what that line is? Y equals x. If two things are a reflection across y equals x, that makes them what? Not opposite. Inverses. That makes them inverses of each other. This one, label with y equals log base 3 of x. And now, let's do a rewrite. 3 to the y is equal to x. That is the same exact thing as that, though. Those are not inverses of each other. That's a rewrite. That's the same equation written in a different way. So how do I get an inverse? Do you remember the inverses are where x and y switch around? So then I just take this and I switch x and y around. And I'm going to make, that'll turn into this. 3 to the x equals y. Y equals 3 to the x. That's this guy. Do you get how these are kind of like cousins of each other? They're related. But if you just rewrite the one, you don't get the other. When you rewrite something, you're not changing it to a different function. You are just rewriting an equation, and they're equal. So this one was equal to this one. And this one are not equal. They are inverses. Okay, so when we did this before, here's a quick 2-second y equals x plus 3. What was the inverse of that? Well, you switch x and y. And then you solve for y. Y is equal to x minus 3. Easiest inverse question in the world. Y equals x plus 3 and y equals x minus 3. Those are inverses of each other. All right. Their reflection over the line y equals x. Let me show you that even. Y equals x plus 3. Would you agree that that's a line that goes through 3 and has a slope of 1? And then here's the line y equals x. And when you change it to y equals x minus 3, you're just going down here. And look at that. They're a reflection of each other across the line y equals x. Okay. So this one was the original. This one was the inverse. How did I do it? I switched x and y and I solved. So a typical question for today might look like this. Y equals 3 to the x plus 2 minus 1. Everybody write that down, please. Is that an exponential? Yes. Do you remember? Everybody take 2 seconds. Sketch what you think not this one looks like, but the standard exponential like 3 to the x. We just said it a second ago. What does that look like again? I can't ask you to tell me verbally because it's too complicated to explain. But how many of you knew it was something like that? Okay, good. Now, do you get this one's been moved? And what does that mean? The 2. Left 2. What does this minus 1 mean? Down 1. So this whole graph would be moved left 2 and down 1. What if, though, I didn't want that? I wanted its inverse. You switch x and y around. Very good. So let me get my eraser out here. Don't need this anymore. And I'm just going to switch x and y. X equals 3 to the y plus 2 minus 1. And then I need to solve for y. Now, in case you've forgotten, you always start by looking for adding or subtracting. So you're going to add 1 to both sides. X plus 1 equals 3 to the y plus 2. In trying to get the y alone, is there anything else I could add or subtract that would help get the y alone? Nope. Therefore, this is the part where it's kind of weird. And how do I get that y set free from up in the exponent there? This is the part where I said in logs, you always look when you get stuck. Look and see if you can rewrite it. So let's get it out of exponents and into logs. So your next step, everybody, write log base 3 of, and then hint, put this in parentheses. It'll matter later. Log base 3 of, and do we just go in order? No, you always jump around. Log base 3 of x plus 1 is equal to y plus 2. And then keep reminding yourself what you're doing. I'm trying to solve for y. So what's the next step? Subtract 2. Subtract 2. Now be careful on this one. There's a fair number of people that think that you just should take the 1 and subtract 2 from it. You can tell by the way I said that I don't want you to do that. Why? Because this log function has been moved 1 to the left and down 2. That would not at all be the same as if you put those together and said that that was minus 1. Okay. So, one more, this one, hopefully entirely on your own. Y equals 5 to the 2x minus 4. Would you please make the inverse of this by switching x and y? And your answer will be a log. Otherwise, you wouldn't be able to solve it. So find the inverse of this equation. Okay, so starting by switching x and y. Next, trying to solve for y. X plus 4 is 5 to the 2y. Next, I'm kind of stuck because I got the y and the exponent. There's only one way to solve that. You rewrite. Well, actually, there's two ways. You could graph both sides and see where they cross. But the main way for this unit is rewrite. So I'm going to use this symbol for rewrite sometimes. I've seen it in our notes. So I'm going to go log base 5 of, you got to jump out to the other side now, over there, of x plus 4, come back over here, equals 2y. And you keep asking yourself, what am I trying to do? Oh, I'm trying to solve for y. So I'm going to divide by 2, and there it is. Now, could this have been a 1/2 in the front instead of a divide by 2? Yeah, and it would probably just look a little cleaner. So I'm going to do it that way. Instead of this divide by 2, I put a 1/2 in the front. All right, it's solved for y, y's alone, and there it is. That's a log that's been moved 4 to the left and has a vertical shrink factor of 1/2. Okay, that's the stuff for today, and I'm going to now show you where your homework is. I'm going to save this Richter scale problem for tomorrow because there may be a small earthquake tomorrow in class. It fits with the lesson, so it's best time to demo an earthquake.